In this video, we'll cover the cross product and triple scalar product. Before defining the cross product, it would be useful to review determinants briefly, as they are a very useful part in remembering the definition of the cross product. So, first of all, well, what is the determinant? Determinant, you can think of it as a function, or you can think of it as an operation that you apply to square matrices. And the operation ends up returning a number. Okay. So for 2 by 2 matrices, the determinant of a 2 by 2 matrix A, B, C, D is the value AD minus BC. You can remember this as being the main diagonal minus the anti-diagonal. Right? These two entries would be the main diagonal, and these two would be the anti-diagonal. For the 3 by 3 matrices, it's a bit more involved. What you have is a relationship, or a process called cofactor expansion that allows you to write a determinant in terms of smaller determinants. So in this for equality, what I'm doing is I'm cofactor expanding along the top row. And so the way that this works is for each entry here, we can, there's an associated subdeterminant that you get by eliminating the row and column that of the entry that you're kind of creating the cofactor out of. Like, you can call this like the cofactor. Each of these terms are cofactors. And so for A, when we eliminate the row and column that A belongs to, we end up with EFHI, which is this. So we end up with this determinant. And when we eliminate B, we end up with the subdeterminant DFGI. And with C, we eliminate and we get DEGH, which is right there. And notice that there's some sign alternation, so plus minus plus. What happens is that you can populate the matrix with an alternating pattern of pluses and minuses, and each of the cofactors, there will be a sign attached to it. So if instead we were to have expanded along, say, the row 2, then you would end up with a minus D something plus E something minus F something as the expression that you get from cofactor expanding. Yeah, so yeah, here I've written that you can actually cofactor expand along any row or column. Typically, well, for our considerations, we will usually be expanding along the top row, just based on how the definition of cross product is. But we'll see an example where I have a matrix that is populated with just numbers, in which case sometimes you might want to choose a different row or column in order to make the computation easier, primarily to just, if a row or column has a lot of zeros, then we can actually exploit that in making the calculation easier. Okay. Oh, and then from here, what's the next line doing? It's just using the 2 by 2 determinant formula in each of the places. Right, so main diagonal minus anti-diagonal gives you that. Same with this, and same with the final term. And then, of course, distributing and rearranging the terms, actually. So after expanding these, what I did was moved all the terms with a plus in front to the front and the terms with a minus to the back. And by doing that, if you actually imagine which ones, how do I want to say this? you can kind of spot a pattern with this. So this is, as I'm writing, it's positive diagonals minus negative diagonals. So AEI, if we sort of visually see where it is, this is, you can call it a positive diagonal, even though it has negative slope. Uh, BFG, it would be these three, and CDH would be these three. So it's, if we kind of allow ourselves to wrap around um, the matrix, it is, we can think of these as positive diagonals. And these last three, they behave in a different way. So actually, it can be perhaps easier to spot it in this picture here. So the main diagonals are the ones that have solid arrows attached, and the anti-diagonals, or the what did I call it? Negative diagonals are the ones with the dashed arrows. What happens here is that this column gets copied over, and same with this column, it got copied over. Right, and so let me come back to this statement. So this is a mnemonic, and the mnemonic fails at dimensions 4 and higher. So if you were to try this same process, you can spot the pattern. But if you try to do the pattern for 4x4 matrices, versus if you cofactor expand for a 4x4 matrix, which will result in 4 3x3 matrix, 4 3x3 determinants that you'd have to compute, you would notice that there's actually terms missing in this mnemonic. So cofactor expanding will always work regardless of the dimension of your matrix, but this mnemonic only works in dimensions 2 and 3. All right, moving on to the cross product. So recall that the cross product, it's an operation that takes two vectors in R3 and it returns a vector in R3, right? As opposed to the dot product that we covered last time, which takes two vectors and returns a scalar. Right? Cross product returns a vector. Okay, so here's the algebraic definition. If we're given two vectors, u and v, with the standard way of kind of spelling out what the components of these vectors are, u1, u2, u3, v1, v2, v3, the cross product is defined by this determinant. Okay, so the first row you populate with the symbols I, j, and k. These are the standard unit vectors. And the second row is populated with the first thing you're putting in your cross product, the first vector, and then the third row is of course the other argument of the cross product. So this is the definition, and then in order to compute this, you actually just run through by cofactor expanding. So when we cofactor expand along the top row, you end up with these subdeterminants, and then computing out these subdeterminants, you would end up with this expression. So I've converted over from the IJK notation to the component notation, the angle bracket notation. Right. Now let's see an example computation. So if we're given specifically u is the vector 3, -1, 2, and v is the vector -2, 0, 1, then the problem asks us to find the unit vector that it wants to call w that is in the direction of the cross product. Okay, so so first we just plug things into the determinant. We're taking a determinant. And so we get this, we cofactor expand. So when we expand this out, let me just slowly talk through this. So the determinant corresponding to I involves these 4 entries. The determinant for j involves these entries, and for k involves these 4 entries. And the sign alternation happens, so plus minus plus when we expand along the top row. Then computing the 2x2 determinants, you do main diagonal minus anti-diagonal, so minus 1 times 1, minus 0 times 2. Next, you do 3 times 1 minus negative 2 times 2. Then you do 3 times 0 minus negative 2 times negative 1. And then simplifying the calculation, you end up with this vector. So this is the cross product. But the problem is asking us to find the unit vector in the direction of the cross product, which means that we need to normalize this vector. And the process of normalizing is we find the magnitude of the vector and then we divide by it, which is why I compute the magnitude here. And as you will recall, the magnitude of a vector is given by the distance formula. You square each of the components, you sum them together, and you take the square root. And so W is defined to be the normalization of the cross product. And so just dividing each of these components by 3 radical 6, the magnitude, we end up with the answer. Okay. Now, there is another way we can define the cross product, which is a geometric definition rather than the algebraic definition that we just gave. So think of these as just another set of properties that we kind of just know this is what the cross product does. So the cross product is the unique vector that satisfies the following 3 properties. It is orthogonal to the 2 vectors that you use to create it. So u cross v is orthogonal to both u and v. U cross v has a length given by this expression, which is actually the area of the parallelogram spanned by the 2 vectors. I'll talk a little bit more about that in a second. And the last property is that it forms a right-handed system, which means that when you do your right-hand rule, the right-hand rule specifies which direction u cross v is pointing in. If you didn't have this last condition, these 2 properties define it up to which direction it's pointing in. So you have length and you have direction and magnitude, but the direction is a bit ambiguous because it could be pointed in some positive direction or pointed in some negative direction. You need the right-hand rule to distinguish which direction it is. Otherwise, there's another vector that is pointed downwards of the same length in this picture. Right? So okay, coming back to this expression. So it's just a possible thing to note that this is the area of the parallelogram spanned by the vectors u and v. The way that you recognize this is to consider geometry and maybe a little bit of trig, right? So how do you calculate the area of a parallelogram? You do base times height. If we let u be the base of the parallelogram, we can find an expression for the height of the parallelogram just by considering trig. So if this side were x, x divided by v, the relationship for these 2 sides is sine. So I don't know, maybe I guess since I started saying it, I'll just write it. So let that side be of length x. Then sine of theta is equal to x divided by the length of v. And so therefore, magnitude of v sine theta is equal to x. All right, so this psi has length that is given by magnitude of v multiplied by sine of theta. And so yeah, that's how we can recognize that this expression is computing the area of the parallelogram spanned by the two vectors. Okay. Right, so using this information, we can answer this problem. So find the area of the parallelogram with sides given by these two vectors, u and v. So area of the parallelogram, you can compute using the magnitude of the cross product. So we take a cross product, and so that process we've talked about already. You populate the entries with u and v in that order, and you cofactor expand and simplify. And then the magnitude is just distance formula again. So square the components, sum them together, take the radical, and you get the answer. Now for algebraic properties. So the first property is very important. The cross product is anti-commutative, which means that if you swap the order of the arguments for the cross product, you end up introducing a negative. It flips the direction of your vector. Next property, it can be good to know, distributivity. So the cross product distributes over vector addition. Next, the scalar multiplication works like this. So you can, instead of scaling up the resulting vector from taking the cross product, you can scale up the one of the initial arguments of the cross product. So, and it's the same thing. Taking the cross product of any vector with the zero vector gives you the zero vector, fine. Taking the cross product of any vector with itself results in the zero vector, okay. And the last one is weird. It almost looks like associativity, but notice that the operations actually change. So this way of rewriting the parentheses is this kind of regrouping is like associativity, except you notice that the dot product has become a cross product over here. So it's not quite associativity. All right. This is basically a multiplication table for ij and k using the cross product. Notice that this first line is the result of part 5, right? Saying that the cross product of any vector with itself is the zero vector. With these three, so the mnemonic is actually the following. You can draw these things out in a circle, like so, and follow the order. If you follow the order of the circle when you're multiplying, so I times j gives you k times k gives you I times I gives you j. I should be saying cross instead of times, perhaps, but yeah, you know what I mean. So if we follow the arrows, then we have a plus. If we are opposing the arrows, we have a minus. It might also be worth mentioning that this is easy to compute visually. So I is in the x direction, j is in the y direction, and k is in the z direction. I'll put hats above all these, just to emphasize they are unit vectors. So yeah, you can compute this pretty quickly just by using your right-hand rule, right? So just lining things up, you can check that I cross j is k, j cross k is I, k cross I is j. Much easier to do it just by manipulating your hand around instead of computing a determinant, although the determinant is also pretty quick to do. All right, moving on. So the cross product angle formula, right? So you'll recall that there was a similar formula involving the dot product. There was a dot product angle formula where instead of the cross you had a dot, and instead of sine you had cosine. So it's neat that there's a version of this for the cross product. Now, the thing about this is that this equation, this holds, this is true, always. But if we try to take inverse sine, there is a problem. And it's to do with inverse trig functions being a little bothersome at times. So I've created a concrete example that illustrates the problem, or the issue that arises. So consider you have the vectors u and v that are given here. A visual depiction of them would be like this. So notice that u and v both have the z component equaling 0. So I'm just using the xy plane as we normally would, plotting things in 2D. And so the z direction is pointed out of the screen towards you, right? And so this horizontal vector, this is the vector u, and the vector v is this diagonal vector, 45 degrees, right, in the second quadrant. So visually, you can see that this angle is supposed to be, what's 90 plus 45? 135? Yeah, or 3 pi over 4. Right, that is the answer that we should get. But if we try to use this to compute it, well, computing the cross product of the two, now this is actually a nice illustration of choosing a convenient row or column in order to cofactor expand easily. So in this case, what I did here is I cofactor expanded. Maybe I'll circle it. What I did was I cofactor expanded along this third column. Right. By doing that, we capture a lot of zeros, which means that those corresponding terms, those cofactors, have a 0 in front of them, which means that they are 0. The only cofactor that we have is actually the one involving k, and the subdeterminant is 1, 0, minus 1, 1, as you can see. And then computing that 2 by 2 determinant, it's the main diagonal minus the anti-diagonal, so 1 minus 0, which is 1. So we get 1k, which is the vector 0, 0, 1. And then we also need to compute the magnitudes of u and v. Well, magnitude of u, you can see, is just 1. Magnitude of v is going to be 1 plus 1 in a radical, so we get root 2. So we end up with this calculation, so 1 over root 2, which you can rationalize the denominator to get root 2 over 2. And then if you think about your unit circle, you can recognize that inverse sine of root 2 over 2 is pi over 4. At least that's what the calculator would give you. You should also hopefully recognize that there are a multitude of answers. There's a whole collection of numbers, such as adding 2 pi k, right? But the calculator will give you just one answer because it treats inverse sine as a specific function with one specific output. It will give you back the value pi over 4, and that is not the right answer. So the problem is that for when your angle is obtuse, this expression, this inverse sine of this fraction, ends up measuring the supplementary angle to the actual angle that we want, this angle over here, instead of the angle that is created from the two vectors. So you end up needing to break it up into cases based on whether the angle is acute or obtuse, which would require some visual intuition about how these vectors appear in space. Which means that this formula is perhaps not that useful. It would be much easier to use the dot product angle formula if you have this type of question of, like, given two vectors, what is the angle between the two? Just use the dot product formula instead. All right. So okay, that's what we have for the cross product. Moving on to the triple scalar product. So this is an operation that takes three vectors, u, v, and w, and returns a scalar, returns a number. Right, and the triple scalar product is usually denoted like this. you've got a cross product followed by a dot product. And the dot product is on the left, but I'm sort of emphasizing the kind of the way you would compute it naively. You would start by taking the cross product, followed by taking the dot product. However, there's a bit of a, I don't know if it's faster necessarily, but it's a way of thinking about this as one single step, which is that you can recognize it as a single determinant instead of taking one determinant and then dotting it. You can just insert the vector u as your top row instead of ijk. And so the triple scalar product, yeah, you can use this expression to compute it. Next, I wrote some properties that this triple scalar product satisfies. This is a really memorable property, actually. The fact that cyclic shifts maintain the answer. So what do I mean by cyclic shifts? I'm shifting the letters around. You see that if I shift to the left, right? So V replaces U, W replaces V, and then U replaces W, like that. We end up with this arrangement of the letters. And then shifting again, we end up with this arrangement. And all three of these are the same quantity. Okay. And well, a single swap. If you swap any two letters, you end up introducing a negative. Now that's easy to see if you swap the two arguments that are a part of the cross product, because as you know, as I've stated, the cross product flips. If you swap the arguments in the cross product, that introduces a negative, right? And then that negative you can then factor out of the dot product, because you can factor scalars out of the dot product. And so this is definitely true. Seeing these other two is, well, okay, the easy way perhaps is, well, we know that cyclic shifts, as I said, they are equal. So if I just cyclically shift this, I know that this, and this are all equal. And then notice that we could go from here to here by just swapping v and u, and by swapping v and u, we introduce a negative. And then for the last one, if by swapping w and u, we introduce a negative. So a single swap of letters negates. Okay. Right. So this is an application for the triple scalar product. So the triple scalar product actually measures something. It measures the volume of the parallelepiped that is spanned by the three vectors. Right. So this is an illustration of a parallelepiped. You can see that it's being spanned by the vectors u, v, and w. And if you end up computing this triple scalar product, and then you take the absolute value, because this is a scalar, it could be negative. We need to take absolute values to make it, a sensible volume, right? Here I'm sort of I copied how you would think about like deriving the fact that this measures the volume of this geometric object. So the idea is that it's just base times height. So the base is a parallelogram, and we, as previously mentioned, the area of the base, the area of a parallelogram, can be computed by using the cross product. It's the magnitude of the cross product. So that's v cross w. And then the last thing that we need is we need the height. We would need the height of the of this parallelepiped. But notice that u may be crooked from the plane that you would create from like v and w. So actually what you need is you need to project the vector u onto something which is perpendicular to both v and w. Well, what's perpendicular to both v and w? The cross product is. So we end up projecting u onto the cross product of v and w. And so we end up with this, right? And we're interested in length, so that's why we have magnitude around that. So this would be, the projection itself would be a vector, but we're interested in the length of that vector. We want the actual height. Right? Um, this next line is actually just the what's it called, the scalar component. Um, it was in the previous lecture. You can check the formula. So uh, the scalar component is this expression, and then the absolute values are there just to get rid of the possibility of it being negative, because in the definition of the scalar component, it could have been negative, in which case that meant that you flipped the direction of the vector. Fine. And then lastly, you split the absolute values over both top and bottom, because both the numerator and denominator of this fraction are actually numbers. So you can split the absolute value over both. And the magnitude is a positive number, so that disappears, and then you can cancel. So you end up being just left with the absolute value of this quantity, the triple scalar product. So that's the derivation. It's kind of neat. Okay, and so now an example. Right, so suppose we're given vectors u, v, and w as given. Find the triple scalar product. That's what it's asking for. So what we do is we insert them into vertical bars. We take a determinant, right? So u is in the top row, v is in the second row, and w is in the third row. Just following the order. And then, let's see, I end up expanding along the row 2. I do that because I want to capture the 0. Right? I end up having one less term in my cofactor expansion. You can see that you could similarly expand, well, I mean, you can expand along any row or column, but to capture the 0, you also could have expanded along the first column. Okay. Right, so then let's see. Let's talk through this. So plus minus plus means that the cofactor with this 2 has a plus in front of it, and then the next one would have a minus, so you end up with a minus here. 2 and minus 2, and then the submatrices, the submatrix corresponding to the 2 would be, we eliminate the row and column, so minus 3, minus 1, 3, 1, which is right there. And then with the negative 2, we eliminate row and column, so we get minus 3, 5, 3, and 1, which is right there. And then computing this, so main diagonal minus anti-diagonal, right? And then same there. And then you just compute this, arithmetic, and you get minus 36. Okay. The volume of the parallelepiped with edges given by u, v, and w. So volume of a parallelepiped given 3 edges, that is the absolute value of the triple scalar product. So we can use the previous computation. We just end up taking absolute value of the previous guy. And so that's how we get the answer. Okay, and that's it.